Welcome to Problems and Solutions. Today we'll solve problem 87 of chapter 22 of Tipler, Physics for Scientists and Engineers. Consider a simple but surprisingly accurate model for the hydrogen molecule. Two positive point charges, each having charge plus E, are placed inside a uniformly charged sphere of radius r, which has a charge equal to minus 2e. The 2-point charges are placed symmetrically equidistant from the center of the sphere, as in the figure here. Find the distance from the center A, where the net force in either point charge is 0. It's a very interesting problem that we can solve using superposition. We always can use superposition in electromagnetism problems. So it's a problem that we can divide in two parts. One is the 2-point charge and the other is the sphere. So we'll solve separately the 2-point charge and the sphere uniformly charged, and then we'll sum the solutions to have the solution for the problem. So separating the two problems, we have 2-point charges and a uniformly charged sphere. We will start solving the 2-point charges. So let's put it, I put it here, and it's very simple to compute the field in the point distance A from the center. So let's start writing the magnitude of the field, the electric field. So we will have E, the electric field, equals 1 divided by 4 pi epsilon 0, the charge divided by the distance 2a squared. So the magnitude of the field, the electric field, it will be 1 divided by 16 pi epsilon 0 E divided by a squared. And we know that the direction of the field will be in the direction of the line join the two forces. So here we have the electric field E. Okay, now let's solve the other part of the problem. Here we have a uniformly charged sphere, and we want to know the field in a position A from the center. So let's draw a surface. We will use the Gauss law to solve this part of the problem. So it's necessary to use a surface to compute the flux in this surface. So let's do it. So here I have our surface, and we can write that the flux the flux in the surface equals to the charge in that surface divided by epsilon 0. To write the charge, we can write the charge density equals minus 2e divided by the volume of the sphere. That's it, 4 divided by 3 r to the third. Therefore, the charge density will be minus 3e divided by 2 r to the third. To compute the flux of the electric field, we consider that the magnitude of the electric field will not vary in this surface because of the symmetry of the problem, and always the electric field and the normal vector to the surface will always be pointing outwards. Therefore, we can write that the flux will be simply the magnitude of the electric field multiplied by the integral of the area, so 4 pi a squared, and this equals to the charge divided by epsilon 0. So 1 divided by epsilon 0, the charge will be the charge density multiplied by the volume of the sphere. So here you have minus 3 divided by 2, e divided by r to the third, multiplied by the volume of the, oops, here I forget something here, 4 pi divided by 3 here. So here we'll have 2 pi. So 2 pi multiplied by the volume of the sphere, 4 pi divided by 3 a to the third. So here we can simplify something and compute the magnitude of the electric field. So here we have, you can simplify here also, and of course here. So you have e or minus e a divided by 2 pi r to the third epsilon 0. So here we have the magnitude of the electric field. This electric field will point inwards because of the sign minus. So here we have electric field pointing inwards. Now we only have to consider both electric fields. What we want is that the magnitude of the electric field, we want that this magnitude be 0. So the net force will be 0. So it's only necessary to consider that the magnitude of both electric fields will be equal. So E A divided by 2 pi r to the third epsilon 0 must be equal to 1 divided by, let's copy this here. So we can simplify this expression, and we can simplify this also, this and this, and we'll have a to the third equals r to the third divided by 8. Therefore, a will be r divided by 2. Here we have our answer to the problem. We simply consider the sum of both fields must be 0, so the magnitude of the fields must be equal. And consider this, we find the solution that we wanted. So that's it. This is the answer of the problem. The problem is solved.